thanks everyone for coming. I like to start always by asking I normally ask who has heard of Spark, but this is the Spark conference, so I probably shouldn't do that. Who's heard of Spark? Raise your hand. Cool. It's more of a test of who's actually listening. Who's written a Spark job? All right, also pretty good. Who's deployed or had a Spark application they worked on deployed to production? Okay, also pretty good. And then who works with time series data outside of Spark? Okay, wow, this is like a huge audience. Never talked to this many people. So you might know all of this content already, but we're going to basically orient this talk around answering 4 questions. Maybe we'll sneak in a 5th one near the end. The first question is, what is time series data? How do we distinguish it from other sorts of data? Does this thing work? Nope. What makes it unique? So, why do we say time series data? Why don't we just say data that happens to have timestamps on it? How do we treat it differently than other types of data sources that we deal with? What do we do with time series data? What sort of opportunity does it give us that other types of data might not? And then last of all, how do we deal with lots of it? And of course, this is where Spark comes in, because in this case, we're talking about big time series data. You need to think a little bit harder about how you lay it out, how you format it, that kind of stuff. I'm a big fan of questions, interruptions in the middle of my talk, so if at any point something is unclear, raise your hand, and hopefully we can get your understanding back on track, or you can help me realize that I've been thinking about it the wrong way the whole time. So time series data, very, very simply, is we have measurements, and we take them at regular intervals, and each measurement has a timestamp attached to it. This is the famous Michael Mann hockey stick graph about global warming. Temperatures were kind of high in the Middle Ages, but they've been declining a little bit ever since then, and then recently they've shot up. What we're looking at here is a univariate time series, so we have a single measurement at every time. When we talk about time series data, we also often talk about multivariate time series, where each particular moment corresponds to measurements on multiple different variables. One thing that often gets confused with time series data that at least in my definition of it, I like to try to distinguish is event data. So, if we have, let's say, logs that are coming out of a production system, each of these logs has a particular timestamp attached to it. Well, that data definitely has a time component. It's not time series data. It's not a continuous measurement at a regular interval. Instead, it's this discrete object that happens to occur somewhere along the timeline. That said, there are many ways to turn event data into time series data. You can say, what are the number of logs that got printed out in the last hour? Then you have time series data, and you can deal with it within this paradigm that we're going to talk about. So this is univariate time series data in a tabular form. Again, we have a bunch of times, and we have a bunch of observations, which in this case we're going to think about mostly as numbers in the real set of real numbers. This is a multivariate time series. Again, we have time as a column on the left, and we have something and something else, real numbers, in these other 2 columns. Any questions about this? Sort of basic ground to stand on before we keep going. Great. What makes time series unique? I think there's 2 sort of main things here that make time series unique. The first one maybe is the most important. So we have this basic assumption in most of statistical analysis. When we think about all sorts of distributions, that data is IID. It's independent and identically distributed. The order in which you take samples is not important. In time series data, these assumptions are often violated. So you have this unique dependency structure that determines a lot of what you're looking at. So you can't say, this point is totally conditioned on the distribution and all the parameters is totally independent from the other points. The points actually occur in a sequence. maybe the most important artifact of this is the fact that what happens now depends on the past, but not the future. So, due to the way that time works, as long as we're not inside the plot of, a movie like Primer or Back to the Future, what happens now depends only on the past, and nothing in the future can affect that. What happens now depends more on the recent past than on the distant past. So this is an assumption of a lot of time series models and a lot of sort of the phenomena that we observe in the real world. For example, if you want to get an estimate of weather is like going to be tomorrow, you're much better to, more likely to get a reasonable estimate if you look at the weather yesterday than if you just look at a mean of weather over all time. And there are time series models like ARIMA models and exponential, moving average models that sort of try to define this mathematically. Often what happens now depends on a season, so there's some periodicity to time series data. There's more traffic on weekdays. It's often colder during the winter months, so we have to think about seasonality with time series data. And then last of all, what happens now often depends on an absolute moment in time. So if there's some sort of discrete event that's really important, like a hurricane, that's going to affect time series data in all sorts of ways at that moment in time and in the moments of time that surround it. Any questions on that? Sweet. Second of all, when we think about time series data, there's this component of human time. So there's absolute time as it goes in this sort of like Newtonian physics sort of way. We're not really going to think about relativity here. But then humans like to impose all this additional structure on top of time, right? We split it up into weeks, up into days. These structures that we split it up into can have different, can refer to different amounts of underlying physics time. So with leap years, leap days, the year 1999 has actually a different number of milliseconds than the year 2000 does. And when you create software that has to deal with time series, a lot of what you're doing is dealing with this this friction between human time and physics time. So this is I think this is MATLAB. I don't remember where this is a little MATLAB piece of code that deals with human time. So that's what makes time series data different and interesting, with respect to other sorts of data sets. What do we do with time series data? What are the unique possibilities that it affords? What are its limitations? So a big one is forecasting. Forecasting, for those who aren't familiar with it, we look at a set of observations about what has happened in the past, sometimes in the more recent past, and then we try to figure out what's going to happen in the future. If anyone has read this book, Super Forecasters, it came out recently. On this sort of like small subset of people that are really good at predicting what's going to happen in the near future compared to most, let's say, pundits and who aren't really good at it. I highly recommend it. It doesn't really have anything to do with this talk, but super interesting. Stripping out time dependencies. So as we talked about, we often build these time series models to capture the fact that our data is not IID. Again, when we say not IID, we're accounting for the fact that what happens now might depend more on what happened a moment ago than just like some abstract probability distribution that all the data is sampled from. Often we can use time series models to make our data more IID. So what we do is we fit a time series model to a data. It might be a ARIMA model, which is autoregressive integrated moving average. It might be a Garch model, which accounts for the fact that not only does our time series vary at different moments, but the amount of variance that we expect to see varies as we go through time. And we'll see clusters of high volatility and then clusters of low volatility. So there are all sorts of fancy and strange effects we can see when we deal with time data. And we fit a model to the data that tries to account for these effects. Then we can take the error terms that are left over after the model. And if our model fits the data well enough, those error terms will be uncorrelated or unautocorrelated with each other in time and not IID. Similarly, there's a bunch of statistical functionality that's sort of just devoted to figuring out whether our data does have these types of time correlations. For example, like a Durbin-Watson test is one of the most basic statistical tests that look for autocorrelation in the data. So we might run statistical tests on our time series, and if we see certain weird effects, try to strip out these time dependencies. And then last of all, a big one that shows up less in maybe the traditional, probably the field that uses time series analysis most is econometrics, right? You're looking at how prices or how various statistics vary, across time. Detecting anomalies comes up less in econometrics and more in fields like fraud, more in the IoT world. You have a series of observations, and you want to be able to characterize what is normal and what happens that's strange in that sequence of things that you see. It's pretty important to take time series. So a lot of maybe naive anomaly detection algorithms will do things like, let's fit a probability distribution to our data, and then say any data points that are a certain number of standard deviations away from the center of that distribution are an anomaly. With time series, you can do a lot fancier things. Again, by looking at things like seasonality. So if you see that it's super cold in the winter, that might be less of a crazy thing to happen than if it's super cold in the summer, and more likely to be classified as an anomaly by your system. Any questions on this stuff before I keep going? Great. So last of all, how do we deal with lots of it? There's lots of existing packages that deal with time series data. In MATLAB, there's the econometrics toolbox. In Python, Pandas has some really nice time munging functionality. R has the zoo and XTS packages. SAS has the whole ETS ecosystem. And so what these packages all offer is sort of a merging of two things. The first is primitives for allowing you to deal with time series data in a way that's different from normal tabular or columnar data. This adds abstractions like human time we're looking at, so you want to be able to understand where April 10th, 1945 is as a number of milliseconds since the epoch. Do fancy resampling and stuff like that, as well as time series specific, let's say, data munching functionality. You might want to compute like lagged versions of a time series that you have, and then put those next to the original versions. You might want to fill in missing data based on proximal observations in that series. So there's this sort of data manipulation, core dealing with time series data set of tools, and then they all incorporate time series statistical functionality. When we talk about statistical functionality, we're mostly talking about time series models, things like ARIMA models, Garch models, Holt-Winters models. And then we're talking about statistical tests. So is our time series data autocorrelated? Does it exhibit various different properties? And so all these different packages have some sort of merging of data manipulation and then time series statistics and models. What none of them have is the ability to operate super well on large collections of time series, work on time series data in a really distributed environment where you have multiple machines. Before we move on, what are some situations where we would have huge time series data? Actually, no, we'll come to that later. Pardon me. On top of these existing time series packages, another way that existing tools deal with time series data is through window functions. So SQL has a whole window functions apparatus, which basically allows you to conduct operations on tables where the output for every particular row depends on not just a single row, but some specific defined subset of other rows. With window functions like lag, lead, and rank, you can do a lot of time-specific functionality by saying, split up our table into a bunch of different time series, and then base the value of each row, not only on the position in that row, but also on the row that came right before it in time. Spark has nice syntax both in Scala and in Python for running window functions, as well as you can write SQL like this in Spark SQL. So last of all, we're going to introduce the time series for Spark project, which is a project I've been working on at Cloudera. It's distributed as the Spark TS package. And as in line with the goals of these packages that show up in these other languages, it has two very related but distinct goals. The first one is provide a natural API for manipulating large-scale time series data. So this covers things like lagging functionality, translating between human time and machine time, manipulating time series data, and taking tables and putting it in a time series format. And then a second goal of provide statistical routines for modeling large-scale time series data. And this is what we talk about with all the sorts of models and statistical tests that work that are built especially for time series data. It has a Scala, Java, and a Python API. Like Spark, the Scala and Java APIs are a little bit more mature than the Python API, but they all work. Let's go back here. Okay, so while we have some time left, let's talk about some of the key sort of abstractions that are built into this Spark time series library. A big question when you think about time series data, especially when you're thinking about time series data across tons and tons of machines, is how do you lay out the data? How does it get laid out in memory? How should the user think about what data points are proximal? So this breaks down into two questions. How do you lay it out within a machine? And then because we're dealing with Spark and we're dealing with a distributed context, how do you deal with laying out data across machines? What goes where? So in our sort of nomenclature here, I think there are a few different ways we can think about laying out time series data. The first one is what I call the observations layout. And this deals with really tall, skinny tables. In this, no matter what our time series data is, even if it's multivariate, even if it's huge, we only have 3 columns. The first column is a timestamp. So every row in here is an observation. The first column is the timestamp for when that observation occurred. The second column is a key, and so that gives us, tells us if we have a multivariate time series, which variable that particular observation corresponds to. And then last of all, we have a value, which is the actual observation, the actual number that we're observing at that moment in time for that particular value. The observations layout is super nice and natural in a SQL context, especially for data ingest. As data comes in from different sources, we can just throw it in as more rows, insert it into this SQL table. But it turns out that it's not actually that great for doing batch time series analytics. Every time that we want to look at any time series or any moment in time, we have to do this big group by, which is expensive in most systems, especially in distributed systems. The second layout we think about is what I like to call the instance layout. And what's interesting about the instance layout is every row contains all the information that you have about one instant in time. So if we look at a row, we have a particular timestamp, and then all the columns are all the different variables, all the different keys that we might have seen in our observations layout over here. So if we have a univariate time series, this is also a pretty tall and skinny table, but as the dimensionality of our time series goes up, the table gets wider and wider. This is a layout that is natural for a lot of traditional machine learning applications. We think of each row as a particular data point, and then we want to train a machine learning model over all of the records. So we might feed data like this into logistic regression or some other algorithm. However, it's not particularly well suited to time series applications. Because the data is naturally partitioned by row, we end up with these sort of disjunctive situations where let's say we have a partition and the partition boundary lies between April 10th, 2015 and April 11th, 2015. It means that if we want to train some sort of time series model that looks at the lags, like lagged versions of each variable, we're going to have to jump across that partition boundary in order to get the information that we need. So last of all, we introduce what we call this time series layout. The time series layout is also somewhat tall and skinny, but within this series column, there can actually be a lot of data. So one column here is the key. And so we're going to have a record in our table for each dimension in our data set. So if we are collecting sensor data for 1 million or 1 billion cell phones, we end up with one record per cell phone. And then we have the second column where each element in this column is an array. And that array is just an array of numbers, an array of observations that correspond to that particular key at different points in time. And then last of all, we have this date-time index, which is responsible for, across the entire table, tying human time or points in absolute time to the observations in these arrays. So it provides basically an index into the arrays. And the nice thing is when you group things into this format, you can form the time index so that one time index corresponds to everything inside of the every record inside of this table. Any questions about that before we proceed? So this is going to look like a glaring gap in my knowledge, but I'm not super familiar with panel data. I would believe that it is similar. So time series in real-world applications. The fact is, in a lot of real-world applications, the length of a time series is not that big. If you look at, let's say, the payments for every mortgage in America, there's probably millions of mortgages, but payments are monthly. So that time series might be something like a few kilobytes for each mortgage. If we look for metrics for every robot in a factory or an investment portfolio with hundreds of thousands of derivatives, even if we're sampling every minute over a year, that's not going to be more than a few hundred megabytes. So in a lot of these applications, it actually makes sense to use this third layout, this time series layout, where we partition along our variables, and then have all the observations, ordered in time, present, for a particular variable in a particular place. This gives rise to the central abstraction of the Spark time series library, which is the time series RDD. A time series RDD extends RDD of string and then vector double. So the string is this generic time series key, some sort of variable identifier, and then a vector double is just a sequence of observations over time. Then we have this date time index that ties indices in this array to absolute moments in time. Here's what a time series RDD sort of looks like laid out. So this is, let's say we have a bunch of stock values at different points in time. We have a few missing values out here, which are represented as nans by the library. And then this is what the distributed partitioning looks like that. So all the green squares end up on one machine, and all the blue squares end up on another machine. And so if we want to say, do something simple, do something that actually might be fairly complicated with a different system, like impute missing values based on the previous value. So for Yahoo right there, we'd want to fill in $60 both for 7 and 8 p.m. We can really easily write that as a projection, as like a map transformation over each record in this data set. Similarly, we can apply fit ARIMA models over each time series in this data set, forecast, and so on and so forth. Here's sort of a sample of what it looks like to use this time series for Spark library. We build a time series RDD based on some of the functionality that's provided for converting data frames or RDDs and either the instance or the observations format into a time series RDD. A shuffle might be involved there. Excuse me. And then we can do time series specific operations, like let's say take a time slice between these 4 days in 2015. We can really easily fill in missing values based on either that previous observation strategy we talked about, or something like a linear interpolation maybe a cubic spline. And then last of all, this last line over here looks at each time series, fits a simple time series model, in this case an autoregressive model of order 1, and then strips out the time dependencies, basically just looks at the error terms from those models. This slide should have been a little bit before, but this is how we build. This is how we build the datetime index. So datetime indices can either be uniform, which means we're looking at regular observations with some known quantity, or irregular, in which case we just have a sequence of dates. The idea of a regular index is that you can deal with sort of strange notions of regularity. So we handle business days, but maybe we have a calendar where it's business days and we leave out certain holidays in the calendar, and regular date-time indices are better for dealing with those kinds of strange ways that we structure time. Statistical functionality, which we looked at before, if we want to fit a do a sort of auto-ARIMA type fit, where we'll have the library figure out the orders of our different ARIMA parameters. We have this little method that can do it for all the observations or for all the time series in our big collection of time series. Same with Garch and a few other statistical models, and same with a bunch of time series stats. So I think we're running low on time, so we're going to breeze through the roadmap and then open up for questions. Where do we want to take this library? What would we like to do in the future? Sort of maybe the most pressing one is that in Spark in general, REDs are going to be dinosaurs. Maybe not immediately, but fairly soon. So I'd like to take the library and transition it entirely on top of data sets, which will give more harmony with the direction that Spark is going. Right now, you can do some windowing stuff. I'd like to give really full, nice windowing functionality, tumbling windows, sliding windows, sessions, full resampling. This is really important. So if you want to, you have data that's daily and you want to make it monthly, or go the other way around, resampling is there for you. And then dealing with very long series. This is where we get into a little bit of the fancier distributed stuff. Right now, we assume that each particular time series is on a single machine. This is a nice assumption in a lot of financial applications, but perhaps not in a lot of IoT applications. So what I'd like to support is basically distributed partitioning of time series. Last of all, there's a bunch of additional statistical functionality that I'd like to add into the library. Vector autoregression is sort of like ARIMA models, but allows you to incorporate more than a single variable in the past. I think that is all, and we have about a minute for questions. So thank you.
Yeah, I have a quick question. Can you go back to the slide where you introduced the time series method of storing?
Yes.
Yep, yeah, that's it. So if you're computing the lag A autocorrelation, does that imply that each executor has k copies of the data set?
So the question is, if you're computing the lag k on one of these series, does that imply that each executor has k copies of that data set?
Yep.
So yeah, you would end up taking each series and replicating it k times to do that lag. But you don't actually store those all in memory at once. You stream over it. So you'd replicate it once, do your thing, replicate it once, do your thing, and so on and so forth.
So then are the intermediate copies of the data, they're deleted?
Yep.
Okay, thank you.
Hi, have you guys considered adding data structures and algorithms to process in the frequency domain as well as the time domain?
So yeah, we haven't really gone much into the DSP, digital signal processing space, because we see that coming up a little bit less, Fourier transforms, wavelet transforms. I was talking to somebody at a big company who's really interested in wavelets and some other stuff, so maybe in the future.
Cool, thanks.
Yeah. Yep. So in that case, you would use a regular date time index. So we showed this like uniform index, but there are irregular indices as well.
I'm just wondering, this model you have right now on the screen, how does it work with time series that are growing? You need to add the point, every day, every second, or?
Yeah. So the question was, how do you work with time series that are growing? So I'd say the model is not super good for it's not a whole like integrated time series database that deals. The idea is you have, let's say, a snapshot of your data and you want to run some sort of analysis over it, explore it, or build some models, and you do that. But it doesn't have like nice abstractions for updating or growing. Right there.
You said that Scala and Java are more mature than Python. What are the things that exist in Scala that doesn't exist in Python yet?
Good question. So the question was, what are the stuff in the library that exists in Scala and Java but don't exist in Python? Probably the biggest thing is most of the statistical functionality hasn't been ported over to Python. This has been sort of less urgent because Python actually has libraries like stats models and SciPy, which provide these stats on their own, so you can use those. But I haven't created a sort of nice integrated ability to access like the ARIMA implementation from Python.
So the ARIMA models and GARC models doesn't exist in Python?
Right, you'd have to use the stats models implementations of those instead of the Spark time series implementations of those. Time frame for data sets? I'd like to do that in the next couple of months. Mm-hmm.
Is there a recommended approach or product to store and retrieve this time series data?
So the question is there a recommended approach for storing and retrieving this time series data? Yeah, I mean, probably the easiest way to store it, especially if you're adding new data all the time, is in this observations format, where you have this tall, skinny table, and then you'd basically use Spark SQL, store it in Parquet, is what I'd recommend. And then there's functionality in the library for converting to and from between observations format and time series layout.
Can you just describe what you're referring to by sessions in the product roadmap?
Yeah. So the question was, can I talk about what I mean by sessions in the product roadmap? So when we talk about windows, often windows are bounded by time. But in other specific applications, let's say we're looking at a user coming to a website and clicking around a little bit. A session is a more natural abstraction. So it ends after maybe some particular timeout or after some sign-out event. And so you want to be able to group things in time based on sort of fancier semantics.
Cool. That's about all the time we have for questions, so let's give a warm round of applause to Sandy.
Thanks a lot, everyone.
Yep.